Whoa, what a cool countdown effect. Hey everyone, how is it going? I see people are still trickling in, so I'm just going to give you another minute to come in. I'll do some, a little commentary, answer any questions if people have questions before we get going. Oh, look at this, Mike James throwing the popcorn and the wine. I like it. Yeah, I hope you're here for a nice time and to learn a little Cassandra in the process, man. We're gonna enjoy ourselves. Um, so you know what? Let's get into it. I'm not gonna for everyone that's here. Thank you for joining. For everyone that shows up late, thank you. Just a little bit less, just a tiny bit less. Those of you that were on time, way better. People that are late, I get it. I'm late to almost every meeting. But you know what? We gotta move. We're not waiting around. So let's throw up some slides and talk about Cassandra 5.0 because this is a pretty exciting time. We're actually voting on the release candidate, the second release candidate for 5.0. And there hasn't been a ton that's been changed in between the two. So everything you're going to see in here is going to be still applicable. And some of the exact details, the precise details, anything that mentions RC1 will be out of date already within just a couple of days. That's a little lame. But you know what? That's just how life goes. Things change and we got to roll with it. So adapt. So let's get started. I will hopefully hit the right button here and bring up my slides. Nice. All right, Cassandra 5 new feature rundown. I got my awesome use of Midjourney over here. I got to be honest, 99% of what I use AI for is for making weird pictures that I can put in my slides. So just purely entertainment purposes. That's all I care about really. So here we go. Let's see if this works correctly. Yes. Who am I? Right? Like, why am I even talking to you? Why are you here? So Cassandra Committer. I've been involved with the project for about 12 years. I used to work at DataStax, Apple. I was principal consultant at The Last Pickle, and I was at Netflix up until April of last year. And that was a pretty good time. All of these have been great times for all sorts of different reasons. DataStax, getting involved with a ton of people that were community leaders was absolutely amazing. Being able to work on consulting at The Last Pickle taught me a ton about hundreds of different environments that I got to work on. Apple, obviously, the scale is insane, and Apple employs some incredibly smart people. So it was really great working there. And then Netflix is another one of those situations where it's kind of in the middle of The Last Pickle, where I had a lot of teams that I worked with directly and working directly with database teams on the Apple side, or sorry, on the Netflix side, really kind of in the middle. So ever since then, I don't have a logo for it here because Rusty Razorblade Consulting doesn't have a logo. I don't need a logo. It's just text. Actually, it's really just because I don't have any branding. It's just me doing stuff. So I'm not that cool. I don't have any marketing. This is my marketing. So yeah, what am I doing now? Consulting, helping people with Cassandra. Still working on Cassandra itself. Trying to get things fixed. I don't really work on major features. I just kind of like work on figuring out how Cassandra works. And the thing that I've really focused on for a long time has been performance. Performance is very tightly coupled to cost and to availability. So as Cassandra has gotten a lot improved over the years, we've had more knobs to tune it. We've made some really great strides in improving the internal performance characteristics of it. I've really kind of been focusing on that, trying to get people to save a lot of money in Cassandra and learn about new features that are coming out and kick the tires and learn when not to use certain things. So I'll be very, very upfront with you about what you should or should not use and how you should use it. Yeah, let's get into it. So new feature roadmap starting at the top. And just a heads up, I don't know if you can hear it in my voice, but I have not been at 100% the last couple of days. So there is a chance that I may end up finishing up a little bit early just to save my voice. We'll see how it goes, though. So I have a couple of glasses of water over here, and maybe that's enough. So First thing that we're going to talk about, Java 17 support. Why do I care about this? There's a couple of reasons. One, the JDK is moving at a pretty fast pace. We're seeing a major LTS release every 2 years. So it's really important that we keep up with that, because we're no longer in this time frame of like, Java 8 was around like forever. Like people are probably still running a lot of Java 8, which is kind of crazy because it came out like a decade ago or more. I forgot when the actual release date was. But newer versions of Java have lots of improvements in them, and for stability, for performance, and around GC. And so the major thing that I'm really excited about in newer versions of Java are our new garbage collectors. So for those of you that worked with Cassandra in like the Java 6 or 7 days, you're probably familiar with trying to get Cassandra to have like GC pauses that weren't completely insane. You didn't have as much memory back then, so you kind of have like a lot of people would put what was in the box, just came with Cassandra into production, and it turns out those settings aren't particularly great for a whole bunch of different types of workloads. So GC tuning became like a thing. Like I've written several posts, I've done several talks about GC tuning. I'll be honest, like it's kind of old and stale at this point. Like doing this sort of thing isn't like how I don't really think anybody wants to have or sees a long-term career in GC tuning. It's just kind of a dumb skill to have to require of people. So what I love here is that what we're seeing in newer versions of the JVM are newer collectors. So we saw G1 GC kind of has taken over from Parnu and CMS. Parnu and CMS has been deprecated, but in newer versions of the JVM, we're actually going to get these two new collectors. We already have them. I shouldn't say we are going to get them. We have them right now. But with Cassandra 5, we have access to them. ZGC, which is now marked as stable, and Shenandoah, which I believe is still marked as experimental in 17, but it might not be. Don't take my word on that. Maybe you may want to just look that up. It's also not an important detail. So what these are huge advances forward in garbage collection in the JVM that allow us to get almost pauseless operation. By that I mean we're looking at like 1 millisecond, 2 millisecond pauses. In most cases, you're going to see pauses that take about that long. So personally, I'm really excited for this. I think Java 21 is going to be an even bigger improvement, because that's where we're going to get generational ZGC. So ZGC right now is not generational. Generational ZGC will actually be really great for Cassandra, because we do a ton of allocation. And for anybody that is kind of familiar with how data gets promoted throughout the JVM, processes that do a lot of allocation are much better suited for generational garbage collectors, because we want to collect that garbage as fast as possible. And so by using generational ones, it means that we're filling up an Eden space and a survivor space. We're able to collect that before it gets promoted into the old. And so because it doesn't have that right now, it's kind of this like mishmash of like new and old, and it's kind of it can take longer to collect. So the newer ZGC is going to be phenomenal in 21, and I think that's what I'm the most excited for. But the step forward is really important, and this will also be extremely relevant. I wouldn't necessarily advise just taking a cluster on 5.0 and taking everything that's the same, and then just immediately switching to Java 17 and one of the new collectors and expect it to just be perfect, because it might not, depending on your workload. There's some other features in 5.0 that will complement this very well, and I'm going to talk about them in just a little bit. Just know that I wouldn't necessarily say, let's just upgrade and use this in isolation. I think that it's going to be best when coupled with some of the other 5.0 features. So I'll just talk about that in just a little bit. One of the things that's really important, though, if you are going to use ZGC and Shenandoah, no matter which one that you're going to want to use, bigger heaps are helpful. So the collector needs to keep up with the with the allocation rate. So if you're doing a lot of reads of like really large values, you're going to be pushing a lot of objects onto the heap. or a lot of large objects onto the heap. And if the garbage collector can't keep up with all of those allocations, then what happens is if it falls behind, then you can end up in a situation where you either have a full heap or it thinks you have a full heap, and then it has to do the equivalent of a full GC, and that's not fast. That you're not seeing a single millisecond pause there. It's actually going to take a long time. So very, very important that you use a large heap so that you don't run out of space really quickly, and you give ZGC the opportunity, or Shenandoah the opportunity to clean up the heap. And this shouldn't be as big of a problem with when we finally move to 21. But in the meantime, if you're using, like I said, some of the newer storage engine features that I'm going to show later, you will get a better result. I think that we have a really good opportunity here, as long as you enable all the right things to get to basically have GC pauses be a problem that you don't really have to care about anymore. Little H2O for me. So this next feature that I'm going to talk about is pretty exciting for an operator. As a user, you might not, if you're just thinking about deploying, you're using the Cassandra cluster that someone else has deployed, you may not really care about guardrails. But if you're an operator and you've ever had some really gnarly situations happen to your clusters, you're probably going to be really excited about guardrails, because they prevent users from doing things that can potentially break your environment. Now, guardrails were introduced in Cassandra 4.1, but there have been a bunch of new guardrails features that have been added into 5.0. So I think it's appropriate to put it here. I think most people are probably not on 4.1 yet. 4.1 is a pretty cool release, although we had some pretty rough bugs early on. So if you're using 4.0, we just released 4.16. I highly recommend getting to 4.16 if you're using 4.0, or sorry, if you're using 4.1, just get to 4.16. It's the latest release. There's a bunch of important bug fixes in there. So if you're not using 4.1, you're probably wondering, what are guardrails? So let me tell you a little bit about some of the new guardrails that are present in here, and tell you why you're going to care about it. Show you how it will help you out. Now, my slides are out of order. Oh my God, hold on. Why did it do my slides out of order? Boom, that is terrible. Why did you do that? Guardrails. Why is it missing all my guardrail slides? Oh God, so embarrassing. Hold on a moment. I don't know what happened here, but we are missing slides. Unprofessional. But that's what you get when you come to one of my talks. I'll just, fill in the time with some banter. All right, here we go. Export. Let's see if we get some working slides this time. All right, we'll take these guys out of here. That's not going to work. Let's put some new ones up. Let's remove that. Here we go. New slides. Jeez. Don't leave. Don't leave. At least this proves you're actually doing a live stream and it's not pre-recorded. Yeah. No, man, no, this is pre-recorded, and I just included that for fun, just to mess with you. Now, the real crazy thing is that I included this part as a smoke screen, so you'd never know, because I figured someone would leave a comment like that. Let's see, did I do it? No, I don't know why this doesn't work. I guess I'll just share my screen. Happens to all of us. So this is Keynote, by the way. So if you want to hate on anything, you can hate on Keynote, because this is absolutely ridiculous. Why would we not have all my slides? Let's try this again. Remove. Present. If this doesn't work, then I swear I will do something better. Let's see. Here we go. Okay, here we go. Trying it. Third time's a charm. It's exciting. Yeah. I appreciate the kind words. Okay. Uploading. It's taking forever. It's a good sign. It means more slides are there. Come on. Here we go. All right, let's just let's see if I'm going to embarrass myself. No, this one will work. This one will work. Here we go. Boom. Add a stage. Guardrails. Nice. Okay. Guardrails. Let's pretend nothing happened. So here are the things that can be really painful, and here are some of the solutions that we have in the form of guardrails. One, a guardrail should be, I check my slides to make sure that they didn't just disappear in the middle of of my talk. That would be a good guardrail to put in place. But on the Cassandra side, we have one that can actually deal with the problem of too many user key spaces. So if you're working on a multi-tenant environment, like if you just let people go wild, you may want to actually prevent how many key spaces users can make, because it doesn't really make sense to just allow people to do kind of anything. Like shared environments, you may not want like 1,000 different teams to be utilizing a single shared environment. It doesn't make sense to do so. So if you put guardrails in place, you can prevent a team from doing too many things. Then you could have a bunch of shared clusters instead of a single one. I'm not really a big advocate for shared clusters. I think a lot of the time they get abused, and I'd rather have the right tooling in place to run multiple clusters. But there's a lot of environments where people set things up by hand, unfortunately, and in those environments they tend to lean towards one cluster in multi-tenancy. If you have great automation, you just spin up another cluster and you don't care about it. But it happens. So we allowed now people to operators to just put in place, hey, we have a key space limit here, so get out of here. You can't create any more key spaces. Not cool. We also have the problem of for anybody that has ever had to deal with TWCS, time window compaction strategy is awesome for time series. So if this is really a specific use case. We're writing a lot of time series data. We're not reading it that often, and we have a TTL on it. So it's really important to have that TTL on it, because there's really not a clean way of deleting the old data other than going in and just like removing it manually using RM and just like shutting a node down, removing a bunch of files, and then starting it back up, which is kind of a crazy thing to have to do as an operator. Usually when people don't have data that's TTL'd and using TWCS, usually it's by accident. And what happens is people will have a table, they won't set a default TTL on it. Oh my God, I lost more of my slides. Where are all my slides? So now I'm realizing this isn't actually a problem with my export. This is a problem with my presentation tool. All right, let's just get rid of this. It's just jumping around. It shouldn't be jumping like that. All right, we're debugging on the fly, so it wasn't my fault. You can actually blame StreamYard for this. Boo, StreamYard. Boo. Move from studio. I guess I'll just share my let's see. There we go. I'll just share my exported slides. Share my slides that work. That's what I'll do. There we go. Look at that. Get rid of this over here. Hide my sidebar. Look at that. Ever the professional. Cool. All right, cool. So now you get to watch me scroll through this. Sick. So here we have our guardrails. They're really easy to use. You just set the key space warn threshold. We already talked about that. TWCS. So basically, what we can do is we can now enforce that a default time to live is set at the table level. So this is really nice. So if you put a default time to live in the table level, you don't have to pass in a TTL with your data. So I've worked in some situations in the past where teams have had multiple locations that they've had these inserts happen, and in like one of them they forgot a TTL. So what this does is this enforces that if you're going to use time window compaction strategy, that you also have a default time to live on the table. So I recommend setting this. To me, this is a no-brainer. If you have if you have a table using TWCS, you should be using the default time to live so you have a consistent so you have a consistent TTL across your data. Scroll down. There we go. What about people writing enormous values? Have you ever seen someone try to use Cassandra as a blob store and put like pictures in there? Dumb. Don't do that. Cassandra is not a blob store. It's a terrible, expensive replacement for a blob store. People love this challenge of just doing things. And it's like, don't put that in production. So is it enough that you have me in some video saying, don't do this? No, of course not. That's insane. Nobody would listen. We don't have enough. I'm not yet in front of the entire world. People aren't always listening. So what you can do as an operator is you can now put these column value size warn and fail thresholds in place. And you can, in 4.1, you actually have the ability to do this with collections as well. So now we're not just telling people, hey, it's best practice to not have like thousands of elements in a collection. You can now just enforce this. Now, this is actually, these are enforced as warnings. They'll just show up in the logs, but it's good to know when they're happening. We don't actually just immediately start, even though it says fail, I don't believe we're actually failing here. It's more like, hey, like this is a really big deal, like stop doing it. But it's good to know about it. What about users dropping key spaces? Do you allow users to drop key spaces? Do you just have whatever environment and you just let people add and drop things at their leisure? I don't love letting people do that. A key space should be created so rarely that it should not be that big of a deal to impose the inability to create or drop it. I think that really this should be limited to power users, especially because there's a replication factor involved. Like you can have some number of replicas that you're going to send your data to. So it's easy enough. We can just say no users are allowed to drop key spaces, and that's it. We're just done. And only a power user can do it. And then on that note about a user like doing weird things, one of the big problems that you could have is a user using the wrong like user putting simple strategy in production, right? If you just like throw a create key space at it, you'll see that simple strategy would be used. You don't want that. Or a user using too low or high of a replication factor. So now we actually have the ability to set the minimum and the maximum. What's the difference to handling this through permissions? Sebastian, I assume that you're asking about the drop key space. So this is kind of a safeguard. So even if you give a regular user the ability to drop a key space, they won't be able to drop it if you disable it as an operator. So it's a little bit of an overlap, and in some cases you might not care, but you may also say like users just are not allowed to drop key spaces. That's it. Oops. Okay, so we got that. Security improvements. Now this is an area that I am not the world's #1 expert in by far. So if I say something dumb here, please drop a line in the comment. But what we have here is CIDR authorization, CIDR. That stands for classless interdomain routing. Yeah, fun. So what this does, this allows us to basically say that certain roles are only allowed to connect from certain applications. And I'm going to show you a couple examples of what that means. Now, first of all, to use this, you have to be using some form of authorization and authentication. So without it, it doesn't. This doesn't mean anything. Typically, for regular users, you are going to have this set up as the password authenticator, or and you're going to be using the Cassandra authorizer. Now, you can plug in whatever you want here. So if you're feeling strong, go ahead, make your own. Have a nice time. It's okay. But for most of the time, you're probably going to be just using the built-in authorization and authentication. There was a bunch of no tool commands that have been added to this that you can see if you just grep for CIDR like I did here. You can see statistics, add, drop, print information around CIDR groups. So the idea here is that you have a group of these CIDR configurations. So for example, like we have application A, and what this update CIDR group does is it says to application A, we're going to add 10.1.1.0 with a 24-bit mask. And then we're also going to set up app B as well. And that's going to go at a different, is going to have a different mask. We can take a look at what's been set up already by looking at system auth. So this is a little bit different than some of the node tool commands that through a lot of the node tool commands. A lot of node tool commands operate only on the existing node. Examples of, there are examples that deviate from it when you kick off a repair that's not a single node operation. But a lot of the commands in node tool do only affect a single node. This is different in that it adjusts the system auth key space. And so what we have here is a new CIDR group where we say, okay, the addresses, the address blocks that we're going to allow here you can view them in here. And so when you create a role, you basically tell it which for a given role, which CIDR groups have access to it. So if you've got your setup so that let's suppose you have your environment set up and you have a VPC for all of your applications, and then you have different subnets allocated for each like service within your application. Those subnets are going to have their own CIDR blocks. So you're going to say that this subnet allows these groups in it. Excuse me. So when you do that, because everything is blocked off, you can say, okay, this application with this user can connect from here. It's just another layer of safeguards. You may say, hey, passwords are enough, or using certificates is enough. This just gives you more options. So security is done through layering. So you're going to want to have, like, if it's really, really important to you that you block off access for certain applications, and it's critical that only certain apps can connect from certain locations, then you're going to want to use this. So it's just, like I said, another layer of security. So moving on, dynamic data masking. So when I looked at the initial feature, when I looked at this, I only saw the first half of this. And so and when I looked at it again, I was like, oh, okay, fine. Like, this makes a lot of sense. So dynamic data masking allows us to it's in the name, mask data. So let's suppose we have a table here with some sensitive information. We go ahead, we have a credit card table, and we insert some information. So now I have my first credit card in here, and it's 111-222, blah blah blah. And so anybody that has access to this table, anybody that can select from this table, can read it. Now that might be okay. Might be okay. But there's a situation where it might not be okay. So if you allow a user to export data from all your tables from one location to another, perhaps you want to mask out some of the sensitive aspects of this. Maybe you only want the last 4 digits to be available. But if you impose that requirement and you don't impose it as an operator, then you're essentially passing the responsibility on to the end user, and they might not be incentivized to do so. This is your data, you want to protect it. So if you don't enforce it somehow, then you could end up in a situation where the user data gets exported into an S3 bucket, and then if you hadn't masked something, maybe that sensitive data gets leaked, and now you're in the Wall Street Journal because you leaked a bunch of credit card data. Um, Whereas if you utilize dynamic data masking, you can prevent certain users from accessing the entirety of certain data. So let's look at how this would look in practice. So we have a bunch of different data masking functions. So you may not be explicitly calling these functions. I'm going to show you how to kind of skip over this in a little bit, but you can see that I've taken the same tables and I've applied all of the different masks to it in this one query. So you can mask the data with a null, for example. So you wouldn't know if there was actually like a credit card number stored or not. The default just applies a handful of asterisks to it. You can replace it with a single question mark. You can replace it with leading or trailing, something. So in this particular case, there's mask inner and mask outer. So mask inner will mask like the beginning. And mask outer starts at the end. And then of course hash. So if we want to put if we want to do some validation that says, hey, we want to make sure these two things are equal, it's nice to have like the same data masked in two different tables. Then you can determine whether or not they're equal without necessarily having access to view the original data. So some really nice options here. But maybe you're wondering, why do I care about masking if I have to apply these functions that doesn't solve the rogue Spark job that like reads all my data and then just dumps it out into a public S3 bucket? Now all the credit cards are stolen. What we can do is we can mask a column. So as you can see here, this is a optional feature. This is an optional feature and you have to enable it. So you're going to want to look for the dynamic data masking enabled property. Otherwise, you're going to get this error that you see right here. It's going to complain. It's going to tell you what to enable. So pretty easy. So just enable that. And then you can alter a column on a table and you can say that you want it to be masked. And then when you say, hey, like, let's make it masked, you can tell it what mask you want it to have. So in this particular case, I've gone through, I've taken my credit card table and I say, hey, you know what? We're actually going to have a read-only user that can read this table, but they only have select privileges on it. So a user actually needs the unmask privilege now in order to view any data that is masked. So for the normal table, you can just go ahead and read it. That's no problem. But if once you define something as masked, you're going to get back the masked version unless you use the unmask option. So let's just take a look. We have this create role read only, and we're going to give it the very, very secret password of Cassandra and allow login. And then we say grant select on key space test to read only. Now I'm giving this user, this read only user, select privileges on this key space. I did not go through and granularly tell it what it can do about masking. So when I log in as a user and I select from the credit card table, I get back this masked version. I can't actually tell what's behind it. This isn't masked at the client level. This is masked at the server side. So from a data governance perspective, from the perspective of people that like just don't want sensitive information leaking all over the place, and you want the ability to control it, you get actually really, really good control now over this mapped data. And if we go back into the Cassandra user, you can see here, the Cassandra user has the unmasked privilege. So I can go ahead, I can read the original data. Now, this is a trusted account. Now, let's suppose that our requirements change and we're okay with granting let's say this read-only account was for a specific, for a specific person, and we say, hey, you know what, this person actually does need access to this data. You can go ahead and you can grant the unmask privilege, you can see it says grant unmask on test.cc to read only. Now, when I log in as that user and it reads the data, it actually comes through and it's unmasked. So again, from anyone that cares about data governance, this is going to be a really, really huge feature. And I've worked with a lot of these types of teams, so I know that this is going to be a very, very widely used feature. But again, requires you to be using authentication and authorization. You do that, and you're gonna be in a really, really good spot. The new math CQL functions. A lot of this is just replacing stuff that comes through and you end up doing in your application. However, this is a building block, and as Cassandra gets more and more functionality, more different ways of viewing the data, it's nice to be able to summarize your data a certain way. So as soon as you start to get, if we ever manage to do really good flexible aggregations or joins or whatever, you're going to want the ability to have more complex expressions and filtering options. So you can see here, these are the new options that you have. Select absolute value. You can apply exponents, log 10, rounding. This is all available now. And again, these are building blocks, so you can put these together. You can do all sorts of weird stuff. So useful building blocks, but probably won't be the biggest thing that on its own, but in conjunction with some other newer features as the database matures, are going to be really helpful. Now we're getting into the tail end of things. So this is where things get a little wild. Storage engine improvements. There are a lot here, and I haven't even listed everything that touches this. I wanted to, but as I can see now, there's just no way that I would have been able to, because I could talk about this stuff forever. Storage engine improvements are awesome. So this is what I focus on from a performance perspective. I do a lot of storage engine evaluation, sometimes patches. I really, really like this. And understanding the storage engine in Cassandra, to me, is critical to being successful with it. Because if you can understand how the storage engine works, you can massively change the cost of running Cassandra. So I've worked in clusters where, because I've spent the time in here to understand what's going on, I've been able to get 10x improvements in throughput and latency. That means that people are able to run the same workloads on a much smaller environment. So a lot of what we're going to see here is going to make this easier. So by allowing us to pack more data into each node, by allowing each node to service more requests, by being more efficient, by using memory more efficiently, we can actually do more with less hardware. So the cost of running Cassandra 5.0 will be less than the cost of running any previous version of Cassandra. This has been a trend that we've had for the last 10 years. We've been able to pack more and more data onto each node. And I want to see 10 terabytes become kind of just a standard thing that everybody's doing, and it's not a big deal anymore. Pushing to 20, 30, 40, that's going to require more innovation. We're going to have to keep going, but every single release is a huge, huge step forward. So let me just give you a quick refresher on how some of the aspects of the storage engine work, because without this, it might not, if you're not as familiar, it might not make sense. So let's look at the right path. So we're not going to take into account the replication, like other nodes, waiting on other nodes, clients, like none of that's, we're literally just looking at the internals of storage engine. So we say, insert some data into foo. Oh, here we go. Dimitri, sorry, joined later regarding Shenandoah. It's declared as production ready since Java 15. Fantastic. Excellent. Thank you for clearing that up. Just as a heads up to everybody, Dimitri here has been on some of my other streams in the past and has more knowledge than I have about some of these internals, which is really exciting. So Dimitri, thanks. I appreciate you chiming in there. Definitely call me out if I miss anything. Keep me honest. So from storage engine perspective, when we insert some data, we insert into the commit log, and then we insert into the memtable. So the commit log is on disk. This is for durability. So if the machine shuts down and we lose the data that's in the memtable, then we still have it in the commit log. The memtable is an in-memory structure. So this in-memory structure is going to be really, really important. older versions, concurrent skip list. Newer versions, we're going to talk about that in just a minute. When the memtable reaches a large enough size, it gets flushed to disk as an SS table. Now, an SS table isn't just one file. So this is really important. I think that it's easy to kind of get confused here. The SS table format is defined internally in Cassandra, but an SS table isn't just one thing. An SS table is actually a collection of files. So with Cassandra, we have primary index, we have compression metadata, we've got Bloom filters, we have all sorts of extra information about each SS table. So the SS table is all of the SS table components put together, all those files. When we have enough SS tables that get flushed to disk, we merge them together through a process called compaction. So compaction will generate one or more new SS tables, but for the diagram's sake, I'm only showing this here. It wouldn't make sense to show how all of them work. But just know that we take some SS tables, we merge them together, and we create one or more on the other end. This deduplicates. If you have the same value or the same key written in multiple SS tables, we merge it and we last write wins. If we have any TTL data that has passed GC grace, then that's removed. If we have any tombstones that are older than GC grace, those are removed. So and TTL data will turn into a tombstone if it's not eligible for deletion. So yeah, that's a gross simplification of what goes on. I kind of skipped over some of the complexity of it, but that's all we need to know for now. So let's talk about the upgrades that we're going to have, because everything in this storage engine has been upgraded. And if I thought about this, I don't think that we've ever had a release like the 3.0 storage engine upgrade was a big deal. But this 5.0 upgrade actually touches even more stuff. It's bigger in a different way. The 3.0 storage engine was huge because it made CQL a first-class citizen. This is amazing because it takes all of the awesome concepts that we have and is like, let's take a decade of learning and like make something that is absolutely amazing. And it's kind of like the best of a lot of different ideas. And one of those big things is Trie Memtables. Now, I have actually tried Memtables a bunch, and I've got some incredible performance numbers out of them. And so I'm really, really excited to share this. So a trie is also known as a prefix tree. So what we have here, so tries and prefix trees are really memory efficient because if we have the same data that duplicates a lot of prefixes, instead of storing that information every single time, what we do is we actually only store the prefixes. Then we have essentially pointers to the from sub prefixes to other sub prefixes. And so when you have let's say 1 million keys that are sitting in a memtable, you're going to have a lot of duplication of those of different prefixes. There's a really good chance that you are, especially if you include, if you're deliberate about what your partition keys are and you have a lot of prefixes on purpose, like if you have a machine name or a date or something like that, and that's at the beginning, then those prefixes are going to compress really well using prefix trees. So what we end up getting out of this is a significantly reduced memory footprint because we are literally just, instead of copying the same data and having it exist multiple times, we're only storing the prefix just once. And so this allows us to pack more data into memory. So that means that for each gigabyte of memtable space that you've allocated, we're actually packing significantly more data into it, or we can pack significantly more data into it. And we can also utilize off-heap memory more efficiently. And the reason why that's nice is because it puts less pressure on the garbage collector. So remember before when I was talking about Java 17 and why I was so excited about it? Pairing Trie Memtables, which I have seen significantly reduce the impact of GC on an environment. Even when it was running G1 GC, I saw GC time significantly reduced. Using Trie Memtables you should have significantly less GC pressure, and it makes ZGC and Shenandoah a lot more attractive. So pairing these things together, this is why I say it's not just enough to just go ahead and slap Java 17 and say use ZGC. You really want to pair it with Trie Memtables because they're the performance on them is amazing. And I did a video, a live stream several months ago where I evaluated them, and I think I was getting 2 to 3x improvement in throughput at the same latency as the old Memtables. So yeah, I was really excited to see that. There's a YAML configuration now. So memtables are also now pluggable. So this is important. From the Cassandra.yaml, you'll see this memtable configuration where we have this default class name. We say configuration skip list trie default. Default. If you change this to inherits trie, then all of your memtables will use the new trie memtables. But you can also explicitly make it happen by saying with memtable equals trie. So if you want to use them for all of them, you can. If you want to only test them out on let's say a small table just to get a feel for it, maybe you have something with like a low TTL or you're writing a lot of data somewhere where you want it to be more efficient, or you want to try it out in a one table at a time. However you want to roll it out, it's up to you. But rolling it out for all of it is possible as well. And if this is interesting to you, there's a really good paper that Branimir published, and it's really good. So if you're interested in that, use this QR code. I should have mentioned at the beginning here, like I put QR codes in my slides to try and get people more information, because there's often way too much stuff that I want to talk about. It's already 9:48. I said I was going to do an hour, and then I was like, I'll do less than an hour because my voice hurts. But no, we're probably going to go longer. So if you want to check out how this works, if you want to see some of the performance numbers around this that he did, check that out. And then there's also, like I mentioned, I did my live stream over here. This was the video. Believe it or not, this is the picture that I used in the title of it, because like I said, I use most of what I do with AI is for silly pictures. So yeah, go drinking a glass of wine. Why not? But check out this video. It's like an hour long. So scroll through it real quick or watch it 50x or something like that if you're curious. But yeah, you can see that the performance of Trie Memtables is there, and it was fantastic. So moving on, BTI storage format. So the BTI storage format, remember the SS table format is a bunch of different files. So it's not just the data file, it's also the indexes. And BTI storage format, the area that we're really going to see the improvement are these trie-indexed SS tables. This is exciting. So all the benefits that I was talking about with memtables, we get with our indexes that are now stored on disk. So the trie structure is actually the keys, is mostly about the keys in memtables. And so again, it's going to be about the keys in trie-index tables, trie-indexed SS tables. So if you enable the BTI format here, then you're going to be able to use the new trie-indexed SS tables. There was a question that came up before. Someone asked me, how will this affect spinning disks? Now, I haven't specifically tested spinning disks because I just don't ever have spinning disks environments, and I really recommend people not use them because they're just archaic. But if you use a spinning disk, I think the BTI format should still be an improvement for you because we're dealing with smaller indexes. The indexes themselves are more efficient. And so by having smaller indexes, we can pack more into memory. So hopefully we should have to do less random IO on here. So I think that we'll be dealing with something that's better, but I haven't looked at every single disk read like I have with the data file format. So this is one of those things where I think it will be better, but you're going to have to test it with spinning disks to see if it's advantageous. There's a whole bunch of information about the format available here. So this was in CEP 25. So if you're really interested in reading it, hit this QR code up in the corner here, and you can read all about the interesting details of how this was done. So every major change that happened in this release was actually accompanied with a CEP that goes through a kind of a proposal process. You can, people work on these things together. They collaborate. They figure out what we're going to build, get input from everybody, and it adds a little bit of bureaucracy because you have to talk to a lot of people about what you're going to build. But in the process of doing it, it solves a lot of problems because we end up with fewer or less likely chance of something that's kind of like half baked getting put in. The more people that look at something, the better. So check out the CEP. There was a lot of thought put behind it, and I have tremendous respect for all the things that Branimir has brought into this release with prefix trees. And then there's another really good post from Branimir as well from last year about Trie Memtables and SS tables. You can get deeper into the weeds and take a look at that there. The next thing that I'm going to talk about is the unified compaction strategy, UCS. So what UCS is an attempt to get rid of the need to have size tiered and leveled, and to some extent time window as compaction strategies that we need to kind of decide on. It takes kind of the best principles of both and the desired outcomes of both and sort of improves upon them. So if you've tried to read through the documentation on UCS, there's a lot of information there, but right now it's a little bit light on details. So as to actually how to use it, there's a lot of details about how it works. But I don't expect everybody to read 17 pages of like deep technical details to understand how to flip a compaction strategy. So what I'm going to do here is I'm going to talk about why it works, and I'm going to show you a few examples of how to use it. So like I said, it's one strategy. So let's just do a quick refresher. So LCS, the thing that's really nice about LCS is that it uses fixed size SS tables, keeps them nice and small. You can specify what size that you want to use. But the thing that's really interesting here is that SS tables are grouped into explicit levels. New SS tables are dropped into an L0. They get compacted together a bunch, and then they move into level 1. Level 1 gets compacted into level 2, 2 into 3, etc. So the size of the SS tables determines how much data exists in each level in that case. And then higher SS tables contain more levels. Sorry, higher levels contain more SS tables. So as you keep going up in levels, you end up increasing the number of SS tables that can be present in that level. So you have a lot of churn in the lower levels, and as you get higher and higher, you have less and less. Now, one thing that's interesting about this is as the data is promoted up through LCS, when you have the same SS table size, but you have more keys compressed into a larger and larger space, but you're taking like smaller and smaller slices of it effectively, you end up with denser SS tables. So if you only had 2 keys, or let's say you only had 10 keys out of a key space of, let's say, 1 million potential keys, and you only have 10, then you don't have a very dense amount of data. You have it's kind of spread across this range of 1 million. But if you put 1 billion in there, then you're actually dealing with like very, very small slices of keys. So as data gets promoted up, it also gets, as just sort of a side effect, it gets denser. And then we have size tiered compaction. So size tiered works by taking data files that are of similar size and merges them together into a new SS table. And the problem here is that this results in massive SS tables. Thinking about things in terms of size is okay when you're dealing with small ones, but when you start to have, I don't know if you ever had like an SS table that's in the hundreds of gigs, it like never gets recompacted. It kind of just sits there. There might be some old expired TTL data it's not great. To be honest, this is like sort of terrible, and it requires a lot of care and feeding in certain situations. If you're if you're using a spinning disc, still, ugh, just stop. But if you are, then you're probably not loving this, because for a lot of right heavy workloads of spinning discs, you can't use LCS. It just won't keep up. And there are situations where LCS just isn't a great fit. So if you do have IO issues, if you do have limited numbers of IOPS, maybe you're using EBS, um, and you want to, uh, you want to be able to store super dense nodes, and then you probably are leaning towards size tiered or TWCS, but sometimes that doesn't fit either. So basically, this results in like a lot of crying and pain. The size tiered kind of is a bummer. But the thing is that we can actually reimagine size tiered as, instead of merging together files that are of a specific, like that are in approximately the same size, and grouping them together and then merging those and writing new SS tables, we can actually think about it as writing fixed size SS tables, but replacing SS tables that have similar density uh, in promoting those. So remember, instead of having huge, 1,000 gig or 1 terabyte data like SS tables, which is just unmanageable, we're going to deal with smaller ones, but break them apart. But by definition, they'll be more denser. So the reason why this works is because now we can think of LCS and size tier compaction as being density focused rather than size focused or level focused. They're both now focused on the density. And so what this does is allows us to switch between SS table options freely. Uh, by still using UCS, we can change the strategy. We can change the options of the strategy without resulting in major, just enormous recompactions. It doesn't become a problem anymore. Um, we know that we have denser SS tables at higher level. So abstractly, these are now so similar that it's really great. It allows us to replace both with one strategy. Um, and by now, you're probably like, okay, John, this sounds great. How do we use it? What's this look like? Maybe you read the documentation, reach the same conclusion I do. What is this? How do I use this? So here's some examples for you. First one, if you were coming from LCS, the easiest thing to do is switch to UCS. You change your compaction strategy to the unified strategy, and then you have something called the scaling parameters. Scaling parameters are pretty interesting. So they basically give you fine grained control over each level. So you can say, hey, like in the beginning, let's do leveled. In the end, we'll do size tiered. If you want to do a lot of churn in the beginning, maybe you have some TTLs occasionally, you want to churn things. But for the most part, like this is probably going to be your starting point. You're going to say, all right, let's start with unified, and we'll put our scaling parameter as L10. This is actually the exact. This will deliver essentially the same characteristics as leveled compaction. And here you can see that I've got this target SS table size is 160. That's just because of the way that it was set up. So if you wanted the same setup as like whatever you're running now, 4.0, 4.1, 3.0, this is what you would use. However, I really recommend increasing this number. So as we go to denser and denser nodes, one of the things that we find is that when you use leveled compaction strategy, if you were to do like 5 terabytes per node, you would have a ton of SS tables, and that's like a lot of files on disk. It's just kind of insane. So what ends up happening is uh, people, as their clusters get larger, they change their target SS table size to be a lot bigger. So you can either go like if you go to 320, you just double it, or you can stick with the new default, which is 1 gig. So this basically aims for 1 gig of files. That means for each terabyte, you're going to have 1,000 SS tables on disk. So just keep that in mind. So when you are scaling up, you're going to have more and more SS tables. So it may make sense to increase that further. It may make sense if you have smaller nodes. You can leave it at 160 or even change move it down. There's a lot of different parameters. I'm not going to cover all of them here. Just know that you can switch from level to this and you get all the benefits. And the nice thing about this, like I mentioned, is you can change these options. Like you can change this 160 meg SS table size because it no longer cares about the size of the SS table. It cares about density. So the density of the SS table doesn't get changed when you say, okay, I want to move to 1 gig. There's no enormous recompaction that you don't have to worry about anything. You just change the number and it only affects things going forward. So honestly, density here, once I wrapped my mind around it, I was like, oh, I see all the advantages here. It's actually quite brilliant and I love it. It solves so many problems. I think that to me, this makes sense to use as a default. I like it a lot. And you can do the same thing if you're coming from size tiered compaction. So size tiered compaction, this has the scaling parameter T4, right? So instead of size tiered, now we're going to just go with density tiered or just tiered. So T4 is going to give you a very, very similar behavior to size tiered, but it's going to use the maximum SS table size of 1 gig. And so what that does is it makes it a little bit more friendly for zero copy streaming, makes it friendlier for backups. Because when you rewrite like a 500 gig file and then you're like, great, now I have to back this up, like that's not fun at all. Like it makes it so that you're kind of constantly backing up more and more like ridiculously large files. It makes it harder to stream efficiently. And it means that like you can't make incremental progress towards compacting a bunch of data. You either do it all or you do it none of it. And it also makes it so that you need to have a lot of free disk space. So by using unified compaction strategy, if you're using size tiered at all, unified compaction strategy is a win. It's like I have only seen it be a strict win. I have not seen a single disadvantage of it. I think it's I think it's amazing. It blows my mind at how cool it is. So what you can do if you're interested in making this the default, you can just say, hey, you know what? Like any table, if you haven't explicitly specified a compaction strategy, it's just going to go ahead and use unified from now on. And it'll use it with the scaling parameters. You can put your own scaling parameters in. That means you could do T4, L, T4. It's either T or L. And you can actually do multiple. So you can say, I want to do size 2 in the lower, level in the higher, or whatever. You can as many levels as you want. It uses the last level. It just repeats it indefinitely. So there's all these other options you can put in. And this is, like I said, this is just really cool. And it will also split SS tables based on predefined kind of borders so that it won't again, it makes it easier for streaming and it kind of separates things out a little bit. So this is pretty awesome. So like I said, we get better node density, better for streaming, just all around performance improvements. So one of the last things I'm going to talk about is storage attached indexes, also known as SAI. So SAI is a really cool feature. This has been talked about for years, and there's been an absolute mountain of work put into this. I'm really excited to have written. So I have some tooling known as Easy Cast Lab and Easy Cast Stress. I was actually going to show that at the beginning, but I realized that it skipped some of my slides. Now that I recall, I'll get to that in just a second. But what SAI does is it allows you to create indexes on fields. So it's not quite what you may be familiar with if you're thinking about secondary indexes. Instead of having like a second global index that lives like a secondary table on your node, what this does is it writes an index alongside each SS table. And there's a bunch of files that come with it. So I flushed this to disk, and you can see there's a ton of stuff here. So you can end up with a lot of files on disk. That's one more reason to use the larger 1 gig files with unified compaction strategy. So you can create, let's say I create this table right here. I have these two fields on it. I have this value text and value int. You can see I create a new index on those fields using SAI, and it's pretty easy to use. You just use it using SAI. So because these are indexes that are attached to the SS table, they're essentially built and highly optimized for partition filtering. So I would not recommend SAI as a replacement for Elasticsearch. If you're saying, hey, great, I can move my search workloads completely over to Cassandra, I would say no. No, you would not want to do that. That is not the use case. Cassandra is not a search engine. I think it's important to actually have decoupled systems. So uh, search is separate from Cassandra. However, if you want to do partition filtering, SAI is pretty awesome because it only needs to look at the search indexes for the SS tables that your data could live in. And Cassandra already has the optimization where it won't look at every SS table because we have indexes for each table for the partition keys. We have Bloom filters that allow us to skip lookups. So basically what we do here is we only look at a handful of indexes. SAI are partition aware. Yes, SAI is partition aware. So if you include a query, so I'll show you in just a sec. Your question, I'll get to it in just a moment. So here's the thing you need to know: non-partition restricted queries are more expensive. If you do a query and you just say, hey, like I want everything, like if you have a user table and you just say, give me everyone in the state of Maine, then it's going to have to look at every index to give you a result. With users, because there's a limited amount of data, like unless you have every like 5 billion users, it might not be that bad. This might be okay for you, but I would not encourage you, if you have a cluster and you have sensitive latencies, I would not encourage you to just start slapping SAI indexes on things and start using them and expect everything to be perfect. It's dicey. And the reason why is because the overhead of your searches, the overhead of these reads, they scale linearly with the number of SS tables referenced. The more SS tables you have to look at, the more expensive the query is. So you don't want this to be a search replacement because it's just not designed for it. And for that, there's a reason why we have this this guardrail here. So if I was running a cluster and I upgraded to standard 5, I would be using guardrail to make sure that people do not use this feature without supplying a partition key. There are a whole bunch of other guardrails that you can use here. So we can say, what the impact is of the actual queries, like how many vector terms we have. I'm going to get to vectors in just a minute. We can even make them the default second index. So if you do not supply using the index type SAI, you will end up just using whatever here is in your default secondary index. So there was a question here about SAI being partition aware. So when you pass a query in and you do let's say where, let's look at my example here. So it's partition aware in that if I pass a query in and I say select from SAI, this table, where partition ID equals foo and value text equals bar, it's partition aware in that it knows, the query engine knows which SS tables are candidates for this data. So it doesn't have to look at SS tables that don't own the data in order to build your result. So let's suppose you had 1,000 SS tables and you don't pass partition ID. It has to look at 1,000 SS tables. There's just no way around that. So it's expensive. But if you pass the partition ID and you have 1,000 SS tables, well, if you're using leveled or UCS, then you know that there's a limited number of SS tables that this data is going to be living in. With leveled or UCS, it's only going to be like 4. So you only have to look at 4 SS tables. So merging that in is actually merging those results back is actually really efficient. So that's why I say think of it as a partition. Instead of using allow filtering and having to read everything and scan everything and potentially reading millions of values, you can put an an SAI index on things, and then you can actually get efficient searching. So a good example of that, if you were to have kind of like a dating thing, and you had a zip code to user, but you wanted to do a search for people who like milkshakes, right? Like I have, my favorite thing is milkshakes. I just want to I want to grab some ice cream and find someone and go sit on the bench and drink a milkshake. Okay, cool. How do I find that? Well, if you have the index on that field, my favorite thing is milkshakes, then I can search for people within the zip code, whatever my zip code is. Doesn't matter, 1, 2, 3, 4, 5, and then then I can search across the SAI index. The reason why it's so good is because instead of having, like, if you're in somewhere like New York where there's potentially millions of people that just absolutely love milkshakes and want to go drink it on park benches, um, you can be scanning through a lot of data. But if you use the index, it becomes a lot more efficient. So potentially useful for things like leaderboards. So if you have a leaderboard for the top scores in a game and you want to see if a particular user is in that leaderboard, you can put the index on the user field. So instead of having to maintain two tables, in this case, you can just maintain one. There's a lot of really good use cases that are replaced. Instead of having to take care of multiple tables, you can throw an SAI index on one of your other fields. And if it's queried, responsibly, then you can get away with packing a lot more data on each node, because this is also going to be more efficient than maintaining two tables. Reduced application complexity. Keep going. Vector search. Okay, so vector search. If you are unaware, there's been a whole thing around LLMs and AI and all the fun stuff that comes with it. And so LLMs are awesome, but they're not always giving great results. I don't know if you've ever gotten bizarro results out of an LLM, but if you provide an LLM with a lot more context, then you can get way better results. And that's what these RAG searches are all about. So before we throw our, if we're going to ask an LLM, let's say about Cassandra, it's actually really helpful to like do a search against the Cassandra documentation, find the most relevant information, and then give it to the LLM as context. It can take that and give you far superior results. So this is from NVIDIA. There's like a whole process here by which you index your data ahead of time. You use a vector search to perform searches on that data, and then you hand it off to your LLM. So this can work in conjunction with them. And the way that this works is through vector search. So what we have is a new type called vector. And so what this is actually a compressed array of floats. And so it's pretty efficient because we know that it's going to be a fixed size, so we can tell the amount of space that it's going to take up on disk, and they're always the same size, because it doesn't make sense to have it not be the same size. Like by definition, it all has to be. So we can either we can create our vector here, and then we can create an index on that vector using SAI. So I've loaded this with some data ahead of time. I have this table called vtest. These are my these are the float values that I've put in there. And then what's cool is that you can select from the table, from those vector values, and you can say, hey, we're going to order this by approximate nearest neighbor, and then we can pass the vector in of where something is. So this doesn't solve the problem of needing to turn a bunch of words into a vector. That you'll need to rely on something else, like LangChain, or any of the libraries that are available. That's not my expertise, but you can, it used to be word to vec, and now there's transformers, and there's been a million other improvements. I'm not an expert in this, so just someone, if you feel like leaving comments that points out everything I'm saying that's wrong, please do. But essentially what we have here is we now have the ability to find the documents for a given table using a secondary index, finding the ones that are the most relevant. And what we can do is we can take those documents, provide those as context to our LLM. And we actually interface with the LLM and say, hey, here's the question that someone asked, but use this additional stuff for context. And so, if I ask a question about compaction, if I just ask an LLM, like, teach me about, compaction, it might teach me about a trash compactor. Like, we don't know what it's going to do. But if we say, teach me about compaction, and we pass the documentation into it, then it can actually do it, and it can answer questions for you. So it may be able to tell you about the different compaction options. It may be able to tell you that things that are specific to Cassandra, considerations that you might have. But without it, we don't really know. So provides additional context. The more context that you can give, the more specific and direct context, the better. So these are really awesome if you're going to want to do like a product catalog, and you want people to be able to ask questions about the product catalog. This is how you would get there. So we can do all sorts of fun stuff here. There are different functions that we can apply here. This, again, not my strong point, but there are a handful of different functions that we can apply to do similarity search, and we can get our numbers out of here. So this is actually the number that's used for ranking. So when these come back, you can see here that this is ranked this way because similarity cosine is these are the exact numbers. So the further you get away from it, the less similar it is. So similarity is essentially a 0 to 1 in number that just tells us how close things are. There are a few guardrails here, so we don't just go absolutely nuts and do like a trillion vectors. Just that won't work. If you're interested in trying this out, Aaron Pletz has a repo, the Minecraft AI assistant. And if you want to see how this works, like, this is, if you want to try the AI stuff and you don't feel like building everything out, probably the best thing that you can do is to find an existing application. Because it's Aaron, it's going to work with on the Cassandra side of things. He's over at DataStax, and he's built a bunch of really cool projects. So this will help you get started. So if you're interested. Now, one of the things that I had in my earlier slides that I'm going to show you here that got cut off was that you can try all this stuff yourself. So I want to encourage people to download this, try it out. So you can see here that this says 50RC1 under releases, latest version. So if you grab this release, you grab a tarball, you can run it on your own laptop, and things are going to run great. You're going to have a really nice time. And if you want to see all the new stuff, you can check out this Cassandra latest YAML, and it will have all the stuff in there that's like the latest and greatest. So really fun. Or you can check out Easy Cast Lab, which I'm going to talk about now. So Easy Cast Lab, here we go. Easy Cast Lab is a tool that I wrote, that I started back when I was at The Last Pickle. So at The Last Pickle, I wrote a pair of tools that became pretty popular in the Cassandra world. One was TLP Stress, and the other one was called TLP Cluster. Put a lot more time into TLP Stress initially. It's a benchmarking tool, and I designed it to solve my need of needing to do lots of benchmarking, usually with a similar like idea. Like, there's not that many workloads that you can run in Cassandra. So the idea was, let's just bake all of the workloads in. I wasn't trying to create the most flexible tool in the world. I was trying to create a tool that was the easiest to use. So then I also created TLP Cluster. TLP Cluster would spin up environments for me. So ever since starting my own consulting company, I've picked these projects up. I've renamed them to EasyCast Stress and EasyCast Lab. Much like a 5-year-old would name something what it is, that's what it is. It's literally just designed to create easy to use lab environments. EasyCast Lab supports all versions of Cassandra since 3.0. Remember, this is a tool that I use for my consulting engagements. I also use it for my trainings that I deliver. So it builds one AMI. You can actually use any version of Cassandra with it. It comes with all the different versions of Java, Python, everything that you need in order to get going. Really, really highly configurable. But one of the things that's really cool about it is that it includes the benchmarking tools that you need. So it includes EasyCast Stress with it. It includes performance tools like BCC tools and the async profiler, which I use heavily in my performance research. It also includes free monitoring from AxonOps. So AxonOps is a company that is monitoring backups, repairs. They have tooling that basically helps you uh, with all the operational aspects of running your own Cassandra environment. Um, so what they've done is they've made uh, the intro version of their app available for free. So you can run up to 6 nodes with this. So when I start an environment with Easy Cas Lab, I have my AxonOps credentials in, and I just get a free 6 node. Uh, I get dashboards, I get all the things that I need to run my environment. So pretty helpful. To get started on it, once you've installed it, and this is available via Homebrew, this is it. You can actually fire up an RC1 cluster using Easy Cas Lab with just this, like 5 commands, and 2 of them are creating a directory and CDing into it. So once you've created an empty directory, you just initialize this directory, you tell it what version you want to use, and you tell it to start. That's it. That's how easy it is to get up and running. Like I said, I use this for my lab environments, for my consulting and testing, and for training, and it's been amazing. You get, like I mentioned before, you get really good dashboards. So these are the dashboards that come with AxonOps. You get a ton of these things. So I've worked with them in the past to help improve kind of the user experience here. Ex-DataStax people, good folks that really get how this works. So it's really cool for me to be able to say, hey, we can spin up environment, and I didn't have to build all these dashboards and all the operational tools. So that went a little longer than I had planned, kind of crazy. So now I'm going to go to questions. And before I go to questions, I'm just going to point out I do have my mailing list sign up here as the QR code. My mailing list is where I put out tips, tricks, information about training, updates to Cassandra. I'll even tell you about when a new version of Cassandra is released, kind of the things that are the most important. Like with 4.1.6, I pointed out 2 issues that were fixed that I consider pretty important. And I'll provide a little bit of details around that. So if you're looking to get information about Cassandra, mailing list is kind of one of the main ways that I'll communicate with people. Pretty low volume, like 1 or 2 emails a month. I don't want to spam anyone. So yeah, just trying to get you helpful information. If you don't want it, don't worry about it. No problem, but you're missing out. So let me just go over here and see if I have any questions. Let's see now. So the last question I have here was, are SAI are partition aware? I think I answered that. No questions here. Oh, thank you. Great presentation. Learned a lot. You're welcome. Thank you very much for joining. All right. Well, it looks like I had reserved half an hour for questions, but I went over, and that's okay because we're at about 90 minutes when things are ending. So I'm going to hang out for another minute or so. If there's any questions that come in, I'll answer them. But if not, we'll just shut this thing down. Everybody can go about their day. You can get 5 minutes back. Maybe I'll put on some cool music. No, I'm not going to put on cool music. Forget that. Forget that. No music. Let's see. Comments. No new comments. All right. We're going to shut it down. Thank you, everybody, for joining. Really appreciate it. Hope you learned a bit. Please reach out if if you have any questions, if you're interested in Cassandra training, you need some help running your cluster, you want to talk about anything. I'm even willing to throw you a free hour of help if you're in a situation you're not sure what to do. I'll happily point you in the right direction. Just reach out. Rusty Razorblade on Slack, or you probably have already found me in a bunch of areas if you're here. So all right, thanks for joining, everyone, and I'll see you around. All right.